So, let us discuss another important topic, that is the third divergence. So, in this topic we are going to understand what is the third divergence and how it is impacting the performance of the GPU. Third divergence is a phenomena that generally occurs in a parallel computing environment, and it basically happens whenever in our code any conditional statement occurs. And because of that conditional statements, some kind of execution path and some other threads may follow the different execution path. So, in a simple terms, I can say whenever the conditional statement is detected in a program flow, then threads within a warp may follow the different execution path to compute its operation. So, basically what is happening here? You can just see in this simple code, here I have mentioned the some conditional statement, and we know that in a warp there are 32 threads and its unique number is T0, T1, T2, T3 and up to T31. So, this number is indicating the unique ID of each thread, and this number basically I am copied in another variable which is called as TID. So, this statement what it is trying to identify, whenever there is a even IDs just like 0, 2, 4 and 30, then these threads almost there are 50% threads. In total there are 16 threads. Out of 32 threads, 16 threads will have a even thread IDs, and it will perform this particular operation, and remaining thread ID which are odd IDs, which have the odd IDs, and this also in total 16 threads, and this remaining 16 threads is going to perform this operation. So, meaning is that within a warp 50% of the thread is following the different execution path, and remaining 16 threads are following the different execution path. So, whenever such divergence occurs in a program, it impacts the performance of the underlying GPU. That means, you can say that divergence cause a more thread to wait while other threads are executing. That means, when one execution path just like this, whenever this operation is executing by the 16 threads, other 16 threads is waiting, and other 16 threads will come into the action to perform this operation once the previous one is completed. So, meaning is the thread divergence significantly degrade the performance of the application on the underlying GPU, or you can say the GPU resources are not utilizing effectively. So, let us discuss the same case here. Program is almost same. You can say that here I also again I am identifying the even threads and odd threads, and even thread is executing this operation and odd thread is executing this operation. So, basically 16, if my program warp will start execution at this time T0. So, 50% of the time the 16 threads will execute the even threads, 16 even threads will execute the one operation, and remaining 16 threads which has an odd thread ID will going to perform the remaining 16 operations. So, that means actually what should happen, all threads within a warp should execute at the same simultaneously, but it is not happening, it is getting divided into 2. So, basically it is a sequential effect. So, you can say it is serialization effect. So, 32 threads is executing sequentially, first 16 threads and next cycle there is another 16 threads are getting executed. Now, let us discuss one of the solution of this kind of thread divergence, and I have just given a name to it, the even and odd thread divergence, because of the even threads and odd threads are being used to execute the different paths of execution. So, how I can solve this problem? So, you can see here I have just replaced that if logic with simple arithmetic operation. You can see the first part here and this is the second part. In first part what is happening? Again I will take the thread 0, I have a thread 1, thread 2, thread 3, thread 4 and so on, thread 31 I have. Whenever the thread idx, so this is my idx value is 0, 1, 2, 3, 4 and so on, you can see. So, when this value is going to is being passed at this execution, so whenever it is odd it is going to generate the 0. This portion is always for even thread IDs, this portion is always 0. So, I am getting the value of 2 is being copied to the multiplier. But in case thread IDX is odd, for example, IDX is 1, then it will generate the remainder is 1 and that 1 is going to add with this 2 and the value of the multiplier will be 3. So, just see here, if IDX is even, then IDX ampersand percent symbol divided by 2, it is always generate the remainder and it is equal to 0. If IDX is odd, then this is going to generate the value which is equal to 1. So, for even IDX this is always 2 and for odd IDX it is always 3. And this 2 and 3 is being passed to the second function here and we are performing the operation, multiplication operation with the getting provided value based on their third index, whether it is even or odd. So, without any if logic or you can say conditional statement, I have performed the same operation. This is one of the solution and this problem will remove the thread divergence issue. In a second case, you can see here, this is also a if statement logic, but here I have just changed the condition. Condition is that I have a 32 threads in a warp, I have total warp has 32 threads. If warp IDX is less than 16, then it has to perform this operation. If IDX is greater than 16, it has to perform the second operation. Again you can see that it is going to give you the serialization effect and significantly it will degrade the performance of your application on a particular GPU. Now, how we can solve that? If you go to the various websites and try to find the solutions for that, some solutions suggest that you can use a ternary operator to avoid the divergence, but in actually if you see here the ternary operator is not a perfect solution here, because this is also evaluating the condition. So, whenever condition evaluation functionality will be added or exists in your program, definitely it is going to create a divergence, but somehow it is much better than the if else logic. So, what is the alternate solution I suggested for this to completely avoid the thread divergence? You can see that this portion which is highlighted with the green color. Here you can see this logic where I am comparing the IDX is greater than equal to 16. If this portion, if IDX value is less than 16, so this is always going to be a 0. But if IDX is greater than 16, it is always going to generate the value 1. So, that means I am just satisfying the case if my just you can I will just go back and we will see the this statement. If my IDX is less than 16, then we have to add the 1. If IDX is greater than 16, then we have to add the value 2. So, just look at this condition. If IDX is less than 16, it is going to always 1, value of V is 1. If my IDX is greater than 16, then value of V is always 2, and I am adding this to my data array. And this portion, this restructuring of the if else logic is completely avoiding the thread divergence. And in this manner, the warp execute in a full lockstep fashion, fully utilizing the parallelization of GPU and improving the performance. Apart from this if else statements, conditional statements, loop divergence also creates the thread divergence. If you look at this logic which is highlighted with green color, so to understand it, just take example of thread 0, thread 1, thread 2 and thread 3. That means the IDX for thread 0, IDX value I will just write here, IDX value is 0, IDX value is 1, IDX value for thread 2 is 2 and for thread 3 IDX value is 3. When this IDX value is being passed to this for logic, for loop, so you can say that for the thread 0, this is going to be 0 and this condition is not satisfied. So, this will not execute. But when for the thread 1, the IDX value is 1 and I is start from 0. So, that means this statement is going to execute one time. Similarly, if we check that for the thread 2, so IDX value is 2 and in this case this thread is going to execute 2 times. So, this statement is going to execute 2 times. Now, similarly check for the thread 3. So, if IDX value is 3 and loop will run over it will start from 0 and go up to the 3 and this statement is going to execute 3 times. So, the point is that when thread ID is 0, so thread ID is going to execute this statement not at all, but when thread ID is 1, it is executing this statement one time. When thread ID is 2, or you can say thread 2 is going to execute this statement 2 times and thread 3 is going to execute this statement 3 times. So, that means the thread number 31 is going to execute this statement almost 31 times, means 32 times is going to execute. So, this is also a kind of divergence and it also may impact the performance. So, it is a responsibility of the developer to identify such kind of loop divergence wherever they have applied for loop or any if logic or conditional statements in the program. they have to identify the solutions for that without impacting the correctness of the result. So, there are n number of problems and there will be a n number of solutions for that. Only thing is that we have to think over it to find the correct solution of the problem. So, in a case both logics are correct, both is giving you the correct output, but only thing is that with the loop divergence you are getting the degraded performance. Means we are not utilizing the underlying resources effectively, especially in a parallel computing environment. So far whatever we have discussed here, so it is giving you some idea or some techniques how to minimize the thread divergence. The first thing we have seen that the restructuring of the code is required. First of all, every developer has to think about the problematic portion of the code, wherever they have applied the conditional statement or any for loop statements, think over it and restructure the code accordingly for the correctness. Another thing is that we can avoid the conditional branching wherever it is possible, like if else statement, instead of if else statement, the developer can use bitwise operations. If you are not finding any good solution for if else statement, then you can think it of how the bitwise operator can be applied to perform the same conditional statement. So, bitwise operator is again is a much high performance rather than if else statement. And apart from that, CUDA also provides some warp level primitives, but I do not think it is a very effective solution. Developers can try these solutions by applying this kind of primitives in their program to manage the thread divergence and communication between the threads in a warps effectively. But in my view, with my experience, that these two solutions, first and two techniques, are very useful and helpful to minimize the thread divergence or completely avoid the divergence. Now, I will discuss another very important topic, that is a misaligned memory access. Because we know that our data is always resides in the memory, and if my program is not able to access the memory properly, or we can say that I am not utilizing the memory properly effectively, then it is definitely going to reduce the performance. So, let us discuss this concept with some analogy. Suppose somebody is running the warehouse. This is I have just taken an example, this is a warehouse, and in this warehouse he has created separate rooms to store some boxes. It is to deliver in a local area. Some persons are managing whatever the boxes are coming, and some person is just pushing all the boxes or keeping all the boxes in these storage areas like this. And one day one owner of this warehouse comes and say that to one of the employee, go and bring the boxes which are red in color. There will be a 5 boxes which are red in color. Five or 6 boxes, you can say, for example, I am taking only 5 boxes, they are red in color. We have to dispatch these boxes immediately, and all these 5 boxes belongs to same customer. Now, person comes to the warehouse, and when the person is coming to get these boxes, so he is thinking that he will go to the warehouse, it will go to the one of the storeroom where the master has indicated that you have to get your boxes there. So, storeroom number 1, he come to the storeroom number 1 and he finds that, but he is coming with the perception that he will get all the boxes in a one room, and he will come, he will collect and he will carry with him. But when he reached to the warehouse and storeroom number 1, he find that there is, instead of 5 boxes, there is only 1 box, 2 boxes are there. Then he go to the second storeroom and he find that 2 more boxes are there, and third storeroom he find 1 box. So, meaning is that this person has to do 3 memory transitions. First he went to the storeroom 1, carry the 2 boxes, come back, and again second time he going to the second store and he is going to bring the another 2 box, and in third he is going to bring the 1 box. So, basically that the boxes are not arranged in a memory in a coalesced manner. Coalesced means that, so all the data are grouped in a single entity that belongs to the same purpose or for the same thing. That is means that is known as coalesced manner. So, but here the 5 boxes that should be in a same storeroom, but it is not like that. It is placed in non-contiguous memory locations. So, they are non-contiguously distributed in a different storerooms. So, that means I can say that the boxes are not in boxes are in a non-coalesced manner, or other words I can say boxes are arranged in a non-coalesced manner in the storerooms. Because of that, the person is going with the mindset like that he will get all the boxes in a one storeroom and he will bring back, and he have to put the 2 more extra efforts to collect all the boxes. The same scenario happens with the memory as well. When CPU generates some instructions with the hope that he will get the data in particular location, but when it is going there he get only the sum of the data, not a complete data there. So, that means CPU has to generate next memory cycle to get the another data, so that it could complete the operation. So, simply I can say it is directly impacting the performance. So, misaligned access cause the multiple memory transition to satisfy a single request. If you map or if you connect this statement with the analogy, when master has instructed one of his employee to go and bring the 5 boxes which are marked in red color. So, basically this request is only one, and the employee has to follow the instructions. So, he was not getting all the boxes in one place because they are arranged in a non-coalesced manner. So, he has to make extra effort to bring all the 5 boxes. So, that is the same thing, multiple memory transitions are required to satisfy the single request. It will increase the latencies and it will increase the throughput as well. Now, I will discuss about what is the non-coalesced memory access pattern with some example of array and with this program. Suppose I have this array is address array is 0 to 9, and each location there is some elements a, b, c, d, e, f, g, h and I, j. These are the elements are present in my, this is the, again I am repeating, this is a memory location and this is indicating the elements that are present in this respective memory location. Now, I have implemented, I have developed my kernel with some this logic, right. Again IDX is a global thread ID of the threads. So, whenever I am dealing with thread 0, its ID is 0 and it is going and fitting it this value here and it is generate the data 0. That means, I have to go to this particular location and I have to bring the data A which is stored at this particular location and you have to store this data A into the variable value. So, I have declared the already variable with the name of value and this register is going to store the value A which I got from this memory location. Similarly, when I am dealing with the thread 2 or thread 2 is processing the same set of instructions. So, for the thread 1 T 1 it will go to this location. I am just right here, it is at thread 1 is handling this, thread 0 is handling this location and at this location it finds a value C and it will bring the value and it will store it in a variable that is called C. Next, if I am dealing with thread 2 and thread 2 will generate, so it is going to indicate this location, this element and it will process and it will bring this element to the variable. So, that means, it is every time it is getting skipped, it is getting skipped and it is also getting skipped, it is also getting skipped every time. So, this indicates that data is arranged continuously, but the way I am accessing it is not a coalesced manner, this is a misaligned access. If suppose at a time I can carry 2 elements of data in one cache line. So, every time I will carry this 2, then this 2 and this 2 and this 2, but when I will carry these 2 elements at the same time in same cycle, only one of these elements I am going to use and this elements I am not going to use and even thread 1 is not going to use this element. So, I am just wasting of my resources. So, I will discuss in cache line impact in coming slides. So, meaning is that the threads in a warp access the contiguous memory location in a coalesced access pattern, but with the stride of 2 the threads are accessing non-contiguous elements in a memory which is leading to the inefficient memory access. So, it is not a problem of storing the element, it is a problem of the logic we have implemented. So, as a developer we have to we also have to think of like how we can implement the logic, so that whenever one memory cycle will go, it will bring the data, required data at in one cycle and we can keep all that data in a particular register for that warp. So, if you see that how it is impacting, it is increasing the latency and it is also decreasing the throughput, means inefficient use of memory bandwidth, and latency is increasing because of the more number of memory transitions. Now, I will discuss about the cache line impact with the help of some matrix vector product example. Suppose I am dealing with, I have to perform the matrix vector product, matrix size is 3 by 3 and vector is also of 3 elements. So, this is a final equation which I am expecting from this matrix vector product. Here you can see that this element, this and this element is representing the row of the matrix. Right. And I have made some assumptions here. Suppose my element size, each element which is storing in this particular location is of 4 byte, as well as I am just considering that my cache line size is of 8 byte. Means whenever I will generate the memory request, so it will go to it will be performed with the help of some cache lines, and cache line is of 8 byte only. And cache lines is very useful transferring the data in form of blocks. So, we will see that how this cache line size is going to impact, because data is moving from memory to cache, cache to L2 cache and L1 cache. So, in that scenario this cache line size is very much helpful. And finally, in registers they are going to get some fixed size of data elements, and that will be decided by the cache line size. So, what is happening here? Suppose I have a cache line size of 8 byte, that means I can carry only 2 bytes at the same time. I have just did some modifications here to make the explanation simple, so that learners can understand how the cache line is impacting the performance. So, now, but for this operation, I want to perform this operation, this row of matrix multiplication with this element of the vector. So, that means you can see the 3 elements and each element is of 4 bytes. So, that means every row is of 12 bytes and vector is also of 12 bytes. This is also required to perform this operation. But cache line size is only of 2 byte, but at a time only 2 bytes can be carried with the help of cache line. So, cache line 1 is going to carry first 2 bytes of the array, you can see here, and second cache line is also going to carry this third element of the first row and first element of the second row of the matrix. But only 3 elements is required to perform this operation and this is not required. So, this portion is going wasted. Similarly, if I am getting the data for the vector, so again it also required the 2 cache lines. So, again one space is going wasted. So, if there are 3 rows, so that means row 1 required 2 cache lines, row 2 also required 2 cache lines and row 3 is also required 2 cache lines here, you can see, to complete this matrix vector product. So, total cache line is required is 6 cache lines required for the 3 by 3 matrix and 2 cache lines is required for the 3 element vector. Now, I have just increased my matrix A into 4 into 4 matrix and also B is also 4 by 4 matrix. So, that means each row has a 4 elements to process and I am just making a continuing with the same example of cache line. So, I have a 2 cache lines, means each cache line can carry 2 elements. So, it has a 4 elements. So, that means 4 elements of the row will be carried by the 2 cache lines. So, every time, but you can see the difference between the previous one. Here I was just wasting one of the portion of second cache lines here, but in this scenario because my matrix size is 4 by 4 and my cache line size is also 2 elements per cache line. So, it is every cache line is carrying the all elements without wastage of any resources. So, this is one of the effective way, and this is a hardware thing I am not going to change, cache line sizes I am not going to change, but only at programming level, if I decompose my problem properly according to the cache line size, it may give improve the performance, effective utilization of the resources. In a one cycle you can get the required data in the registers where you can perform the operations. Now, I have just made the one more modification. Suppose I have, instead of cache line size is of 8 byte, I am using the processor which has a cache line size of 16 byte. Means it can carry the 4 element at a time, and the same 4 by 4 matrix will be processed by this 4 cache line support. You can see that 4 elements will be processed by the one cache line only, instead of 2 cache line in the previous case. Here you can see it is because my processor or my GPU supports the bigger cache line size. Instead of 8 byte cache line size, my processor is supporting 16 byte cache line size, and the elements I am dealing with, it is of 4 byte per element. So, that means one cache line size can carry all the 4 elements at the same time. So, here you can see that to process this matrix, it will take only 4 cache lines. So, this is also improve the performance of your underlying GPU. So, again the cache line size is not going to change because the hardware implemented, but as a developer we have understanding of it, and if we decompose our problems and arrange our data in a collaged manner, so that we could reduce the memory cycles, as well as if we are able to reduce the cache misses, then it is going to improve the performance of the GPU because we are utilizing our resources effectively. Now, I will discuss the cache line and non-cache line size non-collapse memory access impact together. Suppose the memory subsystem loads 16 byte data in a cache line, that is my assumption, and I know that each cache line holds the 4 elements, 4 byte per elements, and I am applying this logic. I am this write 2, which I have already seen the impact earlier. So, what is going to happen here? If I apply the third ID here, third ID is 0, 1, 2, 3, 4 and 5, 6. If you see here, what if I apply this third ID on this logic, and which element I am going to access? It required A1, A3, A5, A7, A9, A11 and A13. Because my cache line size is of 16 byte, means only 4 element. So, first cycle this 4 element is going to process. In a second cache line access, this next 4 element is going to process, and in next cache line this next 4 element is going to process. Now, if you see carefully, when third 0 was handling, here T0, in a first cache line size it will get its value here A1, and third 2, here you can say third 1, which is also handling some element that is present at data 2 position, which is A3. That data is also we have prefetched, or you can that data is also available in the register, and it was fetched in a first cache line access only. So, this data is also present. So, in this case the T1 that does not has to go to the memory or bring the data through the various cache channel. The data is readily available for it. But if you look at this LO boxes, At a time cache line size had carried the 4 elements, but only out of 4 only 2 elements is useful for the thread 0 and thread 1. So, that means 50% elements are being used and 50% elements are not being used. So, they are wasted of the resources, and similarly it is for cache line 2 and cache line 3. But if we make a mechanism or we in our programming logic like that, so in a one cycle, instead of A2 if I am able to get here A3, instead of A3 here if I am able to get A5, and instead of A4 if I am able to get A7 here in a one clock cycle in one cache line. So, then what will happen? These 4 threads will access their own elements in one cache line itself. Means 4 thread, the data which is required by these 4 threads, that will readily available. So, it will reduce the memory cycles and so on. So, this kind of logic we have to implement. So, here we have seen that how the cache line and non-coalesced memory access both are going to impact the performance. If we use the cache line effectively and if we arrange the data in a coalesced manner, so we are going to improve the performance of the underlying resources.